We're going to talk about a couple different kinds of regression models. I know we talked about linear in the last assignment, and this one we're going to talk about exponential, and we're also going to talk about sine function regression. So the first one we have here, we got population. There's a table that has years in the population of Jamestown, and the one thing you have to look out for is a statement like this where it says years since 2000. You want to go ahead and you want to make sure that when you do the years that are provided, that you think of 2000 as 0. So when you input the numbers, these numbers are going to be 2, 4, 5, 7, and 9. Now I'm going to go ahead and pull up my calculator, and I'm going to go to stat, and then I'll put in my 5-year values, 2, 4, 5, 7, and 9. And then I'm going to go to L2 and type in my populations. And again, make sure you're trying this on a calculator if it's available to you. That way you know how to do it later. So I'm going to go to my regression models by hitting stat, right arrow, and then I'm going to go down to 0, which is EXP REG, exponential regression. Hit enter. Go down to calculate. And in this case, it says they want us to round a to the nearest integer and b to the nearest thousandth. So I'm going to round a to the nearest integer. So my equation is going to be y equals 5157.9. So it would be 5158. And then b to the nearest thousandth. So 1,000 has 3 zeros in it. So we're going to need 3 numbers. So it'll be 1.041 to the x power. Now, for b, they want us to sketch a graph of the exponential function from the years 2000 to 2050, and they want us to label the window in our y-intercept. We're just going to do a basic sketch for this. If you go ahead and... So we got, here is 0. Now, we got 5,158, so that's going to be our y-intercept, 0 and 5,158. I'm going to put my equation into y equals, so I got 5158, parentheses 1.041 to the x power. And I need the one for 50, so I'm going to hit second and window, and I'm going to start my table at 50. And then I'm going to go to my table by hitting second and graph. And it looks like for that one I have 50 and then 38,461. So let's say I make this top line up here 40,000 for population. I know we start at 0 and 50, so it's 2050 and 2000. So my first one's at about 5,158. My last point's at 38,461. And again, it's a exponential function, so it's going to curve. So there's our sketch. Now for part C, by what percent does the exponential model predict the population is increasing? You get the percent by the parentheses, what's in the parentheses. And what you want to do is take the part past the 1. It's 0.041. And you want to multiply that by 100. So that ends up being 4.1%. So that means that the population is growing 4.1% a year. Now we're going to do this other one graphically. I know it says algebraically, but we're going to do it graphically, because otherwise you have to use a logarithm for that. So in the case of D, when does the population reach 20,000? Well, we got our table up already. So to the nearest year, when do we get to 20,000? And it looks like, as I move up my table, looks like the closest one is going to be 34. So at 34 years, or in this case 2034 the year, that year is the year that we get closest to 20,000. So there's an example of an exponential regression model. I know we did some linear ones in the assignment before. 2 is just a multiple choice question. Which of the following scatter plots would best fit an exponential? And you'll see kind of 2 and 4 are basically straight lines. 1 actually reminds me of a square root function. But 3, again, this would be an exponential growth model because it's going up. And it's showing that curve shape, but it's not a curve like a quadratic where it comes up and then back down. So 3 would be our answer for this one. And then the last one we're going to look at is exercise number 3. So we got temperature of a chemical reaction changes during the reaction. So I'm going to go ahead and pause the video, and I'm going to put in my new table, and I'll be right back. So I have all my data points in from the table, and we're going to run through the questions for exercise 3. And for part A, it talks about why does this data seem like it might be periodic. And periodic we haven't talked about before, because we haven't done the trig unit yet. But periodic just means that there's kind of a repetition, kind of like a wave, if you're talking about the water, that would kind of flow up and down and kind of cover the same amount of values. So if you look at the data in the table, you'll see that from 0 to 6 it's going up, and then it starts going down till 14, and then it turns and comes back up at 16, 18, and 20. So this kind of motion, like you're going up and then changing the opposite direction, but then you're changing and going back up. Think of it like temperatures on a daily basis. The temperature, there's a low, there's a high, and then it changes based on what time of day it is. So that's kind of how you can describe a periodic function like this, a sine function. So we're going to talk about now part B. In part B, they want us to use the calculator to do a sine regression. So if you go back to stat and calculate, and you press the up button, you'll see there's sine regression is choice C. So we're going to leave all the settings the same, and then we're going to hit calculate. It's going to take a second, and then it's going to give us 4 numbers, kind of like this equation is written here. And they want us to take those and round them to the nearest tenth. So I'm going to put all the values in the correct spots, just like we did for the other models. So they want us to do nearest tenth. So A is going to be 3.9. And then sine. And then B is 0.4. X plus, oops, I actually made a mistake. I'm going to change that plus to a, plus should be a minus, because it's negative 0.7, so minus 0.7. And then we have plus 38.5. So there's our regression model. Now, taking those values into account, they want us to know the range of the temperatures in the chemical reaction. So, to figure that out, what you have to do, you take the value for D, in this case the 38.5. That's kind of our midline. So think of that as the line, if I was to draw that wave back, the midline would be the line that cuts through the middle of our function. And what we have to do is add and subtract the A value to that. So if I take my, in this case, my D value, which was 38.5, and then I add A to it, 3.9, I get the highest value I would expect. So in this case, this is going to be 42.4. And if I do it opposite that and subtract 3.9, I'm going to end up with 34.6. So that means that the range in the temperatures would be from, and I'll write this as an interval, everything between 34.6 to 42.4 I would expect to see for this model. And the other part is talking about the time it takes for the reaction to complete one full cycle. So that whole period that we talked about. Now to find the period, you have to take 2b or 2 pi and divide it by the B value. So I'm going to take the calculator right now, and I'm going to take 2 pi. I'll do alpha y equals for my fraction. So I got 2 second and the caret symbol over 0.4. Okay. And then I'm going to go ahead and enter. And it looks like, based on what we have, we're expecting one wave, one cycle to be complete in about, if we round to the nearest tenth, 15.7 minutes. So that chemical reaction is increasing and decreasing, doing a full wave from one, let's say one top to the other top. This would be your period in 15.7 minutes. And again, the other part, this represents the temperatures. So look for those two values as you're looking at the other questions. You may have to find a range, which you can use the midline and amplitude for, D and A. And if we want to find the period, just remember you have to use this formula that I just gave you for part D.